Yaskawa. Evil.
Hello, this is Matt Pelletier, and let's look at a motion control system overview and learn some of the terminology. This is especially useful if you are new to the motion industry. So first, let's look at the components of a motion control system. The most important component in many aspects being that of the load and what we'd call in this case a ball screw, a belt, any type of mechanical system. But the load can't move by itself. We have to have a motor, a servo motor in many cases. But the servo motor also can't move by itself. It has to be driven through a drive. This servo drive is often referred to as the amplifier or amp. And Yaskawa has a name that we'll put on the front of ours called servo pack. So these terms are all synonymous in the motion world. You'll often hear the word servo, and that servo can be referring to the motor and drive, sometimes together or separate. And one common, you might call it mistake, is to call this drive the controller. And in a sense it is controlling the motor, but the controller, or the logical controller, the PLC, is a separate system. And so I'll call this the controller. The drive just takes a command and makes the motor move as commanded. The controller is what makes the decisions and decides what that command should be. Now, over the years, different manufacturers have done things to combine the controller and drive into one package, or to combine the drive and motor into one package. Yaskawa has done this. We've got a MP2600 IEC, puts the controller together in one package with the drive. But really, no matter how you look at it, we still have these distinct components, whether they're in the same package or not. And finally, here the user interface, we'll call the HMI, the human machine interface. And that could be a nice panel like this, or it could simply be switches and indicator lamps. And then this HMI is used to access and perhaps change different parameters in the controller so that the controller can change the way it commands motion to the drive and hence to the load. So let's start by looking at the controller, because the controller selection often determines the setup and configuration of the drive system. The controller selection can be based on the programming environment, and that's one of the reasons that Yaskawa has moved to the IEC platform. It's an international standard programming environment. Communication is also important, as there may be communication to other systems. Ethernet, DeviceNet, Modbus are some examples. The IEC series has a lot of communication here through both Mechatrolink and Ethernet. And the controller used also affects the servo control features, specifically the tuning algorithms, and then the type of command that's sent from the controller to the amplifier. Again, using the case here of the IEC controller, we would be using the amplifiers in position mode so that we can take advantage of the Sigma 5's advanced tuning algorithms. And other types of controllers may use speed, position, or torque command, and then different levels of the Sigma 5 amplifiers tuning algorithms would be available. Controllers also dictate the number of servo axes. One drive, motor, and load is considered to be an axis. And of course, price is important. Customer specification sometimes just dictates which controller will be used, and the manufacturer reputation, other non-technical criteria. Some of the controllers that Yaskawa offers are the MP2000 IEC family, that's down here. We have the MP2300 SIEC, the MP2310 IEC, which has a little more built-in I/O capacity, and the MP2600 IEC, which is the one I was mentioning that's part of the amplifier all in one package. There's also the MP2000 family, uses a different programming platform and a different operating system, but also very powerful and is capable of a very high axis count. In the case of the MP2200 here, up to 256 axes. 256 servo motors can be controlled by this controller. But Yaskawa also makes Sigma 5 amplifiers that are compatible with the third-party vendors such as Galil, Delta Tau, Omron, and others. And so whether it's network amplifiers or analog pulse amplifiers like we're showing here, the Sigma 5 can interface with just about any type of host controller, including motion controllers, CNCs, indexers, PLCs, you name it. We've got an amplifier that will interface with that controller. And here we're showing example of a controller, torque control mode. CNC controllers are many and varied, but in general they send a speed command, and so we call that speed control. And the most simple type of controller is often found in PLCs, where they'll just send a position command to the controller. This is very similar to a stepper motor, or as it shows here, a stepper card commanding a servo. So with all these controllers, torque, position, speed, we can always do positioning as a system. The question or the difference is just what type of command is being sent between controller and amplifier. A separate type of Sigma 5 amplifier is the Mechatrolink 2. That's an open network interface, and Yaskawa uses that with our IEC and MP2000 series controllers. Other third-party controllers, such as Omron, also make controllers to run servos using this network. This Mechatrolink network can also support I/O modules, and an example of those is the Phoenix bus coupler. So you can use any of the Phoenix I/O on the Mechatrolink network as well. Let's look next at the motor technology. Yaskawa offers 3 types of motor technology: rotary, linear motors, and direct drive motors. Rotary is the typical servo motor. When you think of a servo motor, I think of this rotary type. And linear motors include 2 types. One type is the pre-built, pre-engineered Sigma track, where you just take the whole thing, order to length, and plug in the cables and it runs. But we also sell component level linear motors. 3 types of linear motors: coreless, flat iron core, and T-type iron core, where you've got the magnet track sold in lengths and then the moving coil. You'd build up the system custom or perhaps even mounted straight to the machine. And the third type of motor technology offered at Yaskawa is called direct drive, and it's especially designed with these mounting holes to mount a rotary table. So you can have a very large diameter rotary table on one of these small motors, and the motors don't go very fast. Just about 500 RPM is the fastest one. 300 to 500 RPM is about as fast as they go, but they really have high torque and high inertia, and so very good for rotary table applications. They have a very high resolution encoder. So those work out really well, and you don't have to have any additional gearboxes or other mechanical components as you would if you'd use the typical rotary motor. Of all the motor technologies out there, why a servo motor? Why not an AC induction motor? Why not a simple universal motor like you have in a power tool? Well, servo motors are the most powerful for their size. You get the most torque and speed out of a servo motor compared to other technologies. Servo motors also have very fast response. So if you try to turn the shaft of a motor that's well tuned, a servo motor, it's going to respond and hold that position very tightly. And also when you make it move, it stops, starts, changes speed very quickly. We're talking milliseconds of change time, not seconds. And so this really lends itself well to the motion industry, where we're trying to do motion repeatedly and shave off the few milliseconds here, a few milliseconds there to get the most output possible. With a servo motor, you always have to have an encoder on the back, and that means you always need the amplifier. You don't run servo motors off the line power at constant speed. You need to have the servo drive, and so because of this, you always have a higher cost, especially compared to an induction motor with a VFD system. The amplifiers don't really cost any more for servo versus VFDs, but the motor is definitely more expensive. So you get what you pay for: millisecond response and very small package. Different options available on many of the servo motors offered by Yaskawa. First of all is the voltage. For Sigma 5 we have either the 200 volt motor or 400 volt motor. That doesn't mean that you can't run on 100 volts, it's just that the motor will run on 200 volt, and there are 100 volt amplifiers that run the 200 volt motors. Another option are holding brakes. and that adds a piece to the end of the motor and allows the motor to hold its position even when the servo's off and you don't have any power. Especially good for vertical loads where the load could fall if it doesn't have something holding the shaft. A motor seal is when you have a shaft seal so that chips and pieces of material, cutting fluid, etc. have no chance then of getting into the motor from the shaft side. The motor is very well sealed from the outside, but from the shaft that is an entry point unless you have the additional seal installed over the shaft. And so that's something you'd have to have installed at the factory, the shaft seal. The absolute encoder is our standard option now with Sigma 5. And absolute encoder means that you don't have to home more than one time per install. Once you've homed the motor and have that position, that gets communicated up to the controller, and then the controller always knows where the motor is, and even if the power is off, the battery to the encoder is never off, and the encoder will effectively stay on at all times, and you'll always know then if the shaft is moved even with the machine power off. The keyway is on the shaft itself. It's a little cutout, a little notch cut out of the shaft, and then when you install the servo motor and couple it to the machine, there's a mating keyway, and that does a lot to really ensure that the shaft cannot slip relative to the load. So keyway is an option, and if you don't need the keyway, most of the time you can have a shaft with a keyway anyway. It doesn't bother if you're using this compression type of coupling. There are many performance specifications related to the servo motor, and just a few of them here as an overview I'm going to list. The first is torque, or in the case of a linear motor, force, and that's how hard the shaft can turn. In the case of this motor, more torque means more foot-pounds. Think of a wrench, and the amount of torque you can torque down a nut depends on how long the wrench is and how strong you are. And so by the same token, you have a servo motor has torque, and so there's a measure for that of how hard that shaft can turn. In the case of a linear motor, that's just a straight linear force. When you think of a motor, you think of it turning, and that is a speed measured in RPM, revolutions per minute, of the shaft. And just to get a ballpark idea of how fast servo motors go, the Sigma 5 motors can go as fast as 6,000 RPM. The G series is one that has more torque but less speed, and those max out at around 3,000 RPM. And a third very important specification for servo motors is the moment of inertia, and that's typically referred to by the letter J for inertia and M here for motor, the inertia of the motor. And moment of inertia is a measure of how difficult it is to accelerate the motor from stop due to its mass and its dimensions. So a general trend here is the greater the radius of the rotor inside, the spinning part, the greater the inertia will be. And then also the heavier that spinning part is, the greater the inertia will be. And so the equations of dynamics and physics are used to determine the moment of inertia of the rotor. And the moment of inertia is a very key measurement in the sizing of servos. We'd like to look at the comparison of the load's moment of inertia and the motor's moment of inertia and try to keep that within a certain range for certain types of applications that are very demanding. This concludes the motion control system overview.